Hello, everybody. It's our pleasure to have this week some consortium working on a really hot and advanced virology project, trying to fight outbreaks of deadly viruses, mainly in tropical countries. And we have two of the leaders of this effort with us to give us a complementary kind of presentation on this particular field. So the first speaker would be Stephan GÜNTHER from the Bernhard Nocht Institute of Tropical Medicine in Germany, who is going to give a talk on Ebola virus disease in Western Africa, the outbreak response and operational research. And then after we'll have CARROLL, who is going to talk mostly on sequencing, vaccines development and survival studies from these outbreaks and some interesting conclusions from these studies. So, Stephan, please, you start. Thank you.
So, first, I would like to thank you and Bernhard for this invitation to this really lovely place. And it's for sure the greatest meeting we had in our consortium, in all respects. Scientific and with respect to food and drink and lucky and all this. Unfortunately, our project is finished now. So it was the last meeting. The project started in September 2014. It was a short-term EU-funded project for research. But what I will present you, I will also present some of the research data. But what I will present you is more the basis of this research project, which is the European Mobile Laboratory project, which is like the operational or the public health response project, where we then gather material and get access to patients for the research. So this is our institute in Hamburg, and this is here in the ground level is our BSF4 lab. Here's the virology department, and I also have a very nice view to the harbor. So Hamburg is also harbor city. So we're big ships on the opposite of my office here. So, and the BSF4, of course, means biosafety level 4 laboratory. So this is laboratory where we are allowed to work with pathogens like Ebola, Marburg, Crimean Congo, hemorrhagic fever, Lassa fever, where you usually wear these suits. And the consortium, I will come to this later, was of course mainly composed of all the European countries and institutions who are running, operating these laboratories and working with Ebola. So now let's start. So this I already mentioned was the European Mobile Laboratory Project. This was the clumsy title which was given to us by the European Commission, Establishment of Mobile Laboratories up to Risk Group 4 in combination with CBRN. Yeah, CBRN, because the funding pot came somewhere from CBRN, Instrument for Stability, Capacity Building in Sub-Saharan Africa. And why is capacity building? Because the European Commission asked us not only to set up mobile laboratory capacity in Europe, but also in Africa. So we had actually 3 laboratory units set up, one in Europe and one in Nigeria, and one was meant for Tanzania. So therefore we had, when the outbreak started, we had 3 laboratory units available for outbreak response. So everything was funded by the European Commission. And these are the core partners in this project. As mentioned, the project started in 2012. So we had 2012, 2013 to prepare. Of course, no one of us was aware that we will have in 2014 an outbreak of this magnitude. Yeah? So we thought, okay, well, we do the project, we set up everything, we train the people, but realistically, no one of us assumed that we will ever go with these units to the field. But so, you know, this is sometimes reverse of Murphy law. Sometimes everything works. So these were the partners. So this is Mike. So we did the second talk here in Porton town, the BSF4 labs in Rome. Rome is BSF4. This is Hamburg. then very fast. This is in Marburg, in Lyon, in Spiez, and in Sweden. So all these were essentially the partners of this project and provided their expertise. And this is how we work. This is Petra in our lab, and this is how Miles is working.
That's me.
It's yours. So, okay, so if we were talking about mobile laboratories, then often people think it's like a truck, and you have a big container on the back, and then you drive with the truck. And this concept has also been implemented in West Africa, for example, by our French partners. But of course, this takes time to bring it to the field. So we need something to respond within days. Say, okay, now you have to go. So in 2 days, please deploy a laboratory. So the concept is very simple, and it's not from us. It's actually is copied from the Canadian colleagues in Winnipeg. They have invented this very light type of mobile lab. So you have some boxes, about 20 of these boxes, and you take everything you have in your lab and you just put it in the boxes. Go book a commercial flight, and then you check in it as excess luggage. So nothing of this is more than 32 kilogram, because this is the maximum weight you can have for a piece for check-in in an airplane. So we have these 20 boxes, and at the heart, of course, there is because we are talking about Ebola Lassa, is a glove box, which is actually the equivalent to our BSF4 lab. So it's like this one. It's like this one, but a bit smaller. So and this is fine to work with to inactivate BSF4. So of course we are training workshops, mock deployments, and we always said we go with GORN. So we are GORN WHO partners, and we work with this is GORN means Global Outbreak Alert Response Network of the WHO. So that we are a partner of this network. So everything was ready by 2013. Of course, no one was expected we will have an outbreak, but what suddenly happened was that, and I still remember because I was in holiday skiing in Austria, so what Germans usually do in February, March. So MSF called me and said, Stephan, we have here some samples from Guinea, and we think it's not Lassa. So Guinea is Lassa endemic area for Lassa. Everyone would say, okay, hemorrhagic fever in Guinea probably is Lassa. But he said, no, it's probably not Lassa, it's something else. It might be Ebola. And we said, okay, fine, and send these samples to us to the network in Europe. And they sent samples to the BSF4 lab in Lyon and to Hamburg. And indeed, it turned out very, very quickly that they were positive for Ebola virus. We could also grow this virus, which was very important to have the virus at hand, because then we distributed this virus to all BSF4 labs across the world for studies. And of course, we quickly sequenced this virus, and it turned out that this virus was the very first paper. Here is the Ebola virus, and these are the Ebola virus from Democratic Republic of Congo, from Gabon, so the known viruses. And this is still within the clade which we call the Zaire Ebola virus. And don't be confused, because the taxonomy changed now. We are now only talking about Ebola virus. So this Zaire Ebola virus is now called just Ebola virus. While this virus, which was called Sudan Ebola virus or Western Ebola virus, is just called Sudan virus. So it's completely confusing to us as virologists, but these are some guys in the taxonomy committee made this decision. And it also confused a lot of people in Africa, because we said, oh, it's a new Ebola virus, but means a new strain of Zaire Ebola virus. No one understood. So, but clearly it is Zaire Ebola virus. So, and then after we confirmed this diagnosis, then WHO said, okay, we know you have these laboratories ready for deployment. WHO, we have been always in contact with them. No, now go, take your laboratory. And this was the first time that actually Europe was asked at all to deploy these laboratories. So before, it was always the Center of Disease Control in Atlanta or our Canadian colleagues. So we were really, my blood pressure was very high because we only did training, so we didn't know if it really works. And then we deployed on the 26th of March. We had with us a commercial assay, or actually was a prototype of a commercial assay for detection of Ebola virus, which was also developed with a company in Hamburg, and which worked very well in the field. So these are the boxes. This was the first team. I'm here. I think this is me. So in the airport in Munich. So it was about 4,000 euro to pay for the excess luggage, but everything worked fine. So we arrived in Conakry, then went by car to Gekedu. So this is just how we. This is the lab. So this is more national transport facilities. So we went by car to the epicenter of the outbreak in Gekedu, where MSF already had set up a treatment center. So this is the lab boxes. This is the treatment center. So this is the fence of the treatment center. So here there are already the patients. So they were really waiting for us to do the diagnostics on site, because you know why do we need the diagnostics? Because no doctor can diagnose an Ebola virus disease based on clinical features. It's impossible. The main clinical features of Ebola virus is vomiting and diarrhea. So that's it. Yeah? So therefore, no chance. You need a laboratory to tell you this is Ebola disease or this is something else. Because otherwise, you don't have enough capacity in an outbreak to put everyone, even based on suspect, to put everyone in these isolation or treatment units. So MSF had set up this tent for us. We were actually semi-happy about this. We thought about having a stable structure. Actually, later on, we moved in a stable structure because the tent becomes very, very hot at noon. It was not so easy for the teams to work, but we managed to set up the lab in the tent. This is Erna from Munich. So the first team already was in mixed. So he's from Lyon. She's from Munich. So this is sample reception, and this is the glove box, which I told you is a foldable, so it's easy to transport. So we can expand it. The samples go in. Now we have a second generation, which is easier to manipulate, and then you inactivate the sample in the glove box. So this is step number one. Is the inactivation of the material, and this is just a simple buffer which is used in regular diagnostics. Also here, so every diagnostic department is using this type of system. So the inactivated material is then moved out of the glove box, and then you have a very simple regular molecular diagnostic work stream with real-time PCR at the end. This is Silvia actually coming from Rome. So, and these are all the sites where we deployed during the last 2 years. So this was the initial site of deployment was here in Gekedu. So this was the first site. We stayed there until April 15. Then we moved from there to Korea here, because then the outbreak was over here. Then in September 2014 we set up the second unit here in the north of Liberia, which later on moved then here to Hastings here in Sierra Leone until end of 2015. And then I mentioned that we had a third unit which was already deployed to set up in Nigeria to support public health response in Nigeria. And the Nigerian team, actually, maybe you know, there was an imported case from Liberia. So there was someone coming here to Lagos, and there was a lot of fear that now the disease is spreading in Lagos. I don't know if you know Lagos. This is a 10 million people, or even 20 million people city, totally overcrowded. If you have Ebola in this city, this would be the super GAU. So everyone was very afraid. But fortunately, we had the lab. We had the lab here it was here in Edo State. There it was stationed with our colleagues, and we could rapidly deploy this here to other sites to do the diagnostics. Because then there was a spillover from Lagos. There was a guy coming from here to Port Harcourt to get treatment, infected the next doctor, and the doctor infected the next doctors. So there was a small cluster, and all the diagnostics could be done here. And this was also very good training for our Nigerian colleagues. So we joined them at this mission, a very good training for them, so that then WHO and the European Union said, oh, you did so well here with this small outbreak, please deploy this lab to Freetown. So, and then they moved in December to 14, so when Nigeria was safe, they moved with this unit here to Freetown and to Cambia, and our Nigerian colleagues then managed this lab unit totally on their own. So we just provided all the support, all the reagents, everything, and the payment, the money still came from the European European Commission, small contribution from African Union, but otherwise they manage completely on their own. So a very good example of in capacity building in Africa. So, and they just moved back here in March 2016. They tested 5,000 samples. And actually our lab here in Conakry there's no end date here because the end date was just 2 weeks ago. So just 2 weeks ago we closed the lab. It was then in Conakry, in Longo. We closed the lab because now its surveillance phase in Guinea is finished. So, and this is a summary. The teams which we deployed were usually 4 to 5 persons. We stayed 4 weeks in the field and were collected from all across Europe. So unfortunately, I think we had no Greece. Next time we have to make more noise. Yeah. So also because it was not easy during the outbreak to recruit staff for these labs. You see, there were more than 60 teams. Every team is 3 persons, or more 3-4 persons, or 200 persons, who also had to be trained. Yeah. So PhD students, postdocs, technicians. Yeah. So everyone who can do pipetting and is not afraid of Ebola, so could go to the field, no problem. We tested 25,000 samples, 3,500 are positive, and these 3,500, of course, were also our working basis for the evident project, for the research project. So, and now I switch a bit. I present you just, let's say, two examples of research which we had done in the field, mainly in the late stage. Might also talk a bit late stage, but also during research during the epidemic. And one of the main concerns at the end of the outbreak was the persistence of the virus in various body fluids. So this was realized during the outbreak. The virus is very sticky, does not go out of the body, even to probably the survivors are immune, but still virus is persisting, a bit like herpes virus. And the virus usually tends to go to glandular tissue. So we find it in breast milk, but we find it also in seminal fluid, CSF. So, and there was, of course, the concern about persistence in seminal fluid because it means it could be sexually transmitted even after the outbreak is over. So we followed together with colleagues from Dauda Sissoko is the first author from INSAM. He followed a cohort of 26 men who were discharged from the treatment centers. They were followed for about 200 days after discharge, which is about 250 days after onset of disease. 130 seminal fluid specimens were collected, and then we also did some studies to test for the infectivity, but this was of course then done in the BSL-4 lab. While all this testing was done in the field with our EM lab units, so that we could also immediately inform the public health authorities and the survivors. So you are still positive, please be careful with your sex, with your life, yeah, with your own, not to transmit it. So these are the decay curves, the clearance curves. So this is the day after onset. So these are 8 representative patients, survivors. So they all survived. So what you see here in red is the virus in black, so which is rapidly cleared in all those. So, and then of course when it's negative, the patients are discharged from the treatment center. So, and this is the virus in blood. So this is the CT value, but this roughly corresponds to log units of virus. So this means this is detection limit, and this is a log decrease. So, and you see this is very nicely, you see that in all these patients, they have a virus detectable here for more than 200 days, here 200 days, about 200 days here. A virus detected by PCR. So, but it means detection of RNA. It does not mean the virus is infectious, but it means there is at least virus genome detectable. And then we tested for infectivity, and if there is a plus here, means that the virus is still infectious, and we used a sensitive system in BSL-4. We use SCID mouse, completely immunocompromised mice, infected these mice with seminal fluid specimens, and then looked if the virus could replicate in this. It's more sensitive than cell culture. And you see that we could prove infectivity in some cases more than 200 days after onset of disease. So it means this virus is very likely still infectious virus. It's not just shedding of RNA in seminal fluid. And it's already obvious that this is here like a clearance kinetic, and then colleagues from INSAM, the bioinformaticians, so use this then to draw these decay lines. So these are first order decay, because this is a log scale here. So then if a straight line is the first order decay, and from all this they calculated that that the clearance rate of the RNA from the seminal fluid is about half a log RNA units. So this is arbitrary units, half a log unit per month. So it's a very slow decay. And then, of course, from these data you can calculate what is the chance of clearance. Here, 50% chance of clearance in a man is 115 days, so it means 50% of all men still shed virus until 115 days after onset, and 10%, 90% chance of clearance about 300 days means 10% of the men still have shedding virus RNA, probably infectious, after 300 days. So that means there is a long chance of still of virus sexual transmission by sexual route. And other colleagues then from London, they use then the incidence rate from the epidemic and calculate so how many men are probably still shedding virus in the epidemic. And they went here, according to these calculations, by July 2016, so just now. Yeah, even though the outbreak was mainly over here in 2015. Yeah, so by July, the last man cleared virus. But the prediction intervals are very wide and go into 2017, which means we have to be very vigilant in these countries. So the surveillance systems must still be operational, yeah, because otherwise you might miss a sexual transmission and a new cluster. And this is not only theory, but this is really a real threat that this happens. Was actually confirmed, was shown by a case we had here in a case here in March 2016 in Guinea. Guinea was in December. Guinea was declared free of human-to-human transmission of Ebola virus. So no more cases in Guinea. So, but what happened is, and this was very far in the forest area of Guinea in Zerrekore, there were 3 deaths. And then from these 3 deaths, there were 3 cases who became infected because they had contact to these 3 deaths. The 3 deaths could not be investigated because they were buried already. But then the public health authorities became aware that this looked like a transmission chain. Yeah? And this disease looked like Ebola virus. Yeah? And they said, oh, so we have a new cluster. Well, what does it mean? Did we overlook some transmission chains in the forest area? So some hidden transmission chains which were not detected. Yeah? Or where does this virus comes from? So no idea. Yeah? And Miles will introduce you into all the sequencing efforts which we had during the epidemic. So what was the clue is that these cases we did because then we had a sequencing facility with us in Guinea. So we rapidly sequenced the virus from these 3 cases. So as I mentioned, so they were no longer available, but these 3 cases, the virus RNA was available. So we did in the field full-length sequence. And then, and I have to go to this slide here, a lot of sequences had been generated during the epidemic. About 10% of all cases had been sequenced. Miles will provide you with the details of our contribution to this, not only from us, but also other partners in the field. It's the best coverage or sequence coverage ever for an outbreak. So, and with some luck, yeah, if you have now, oh, it doesn't go back. No, it's stuck. No, it's working. Yeah. And with some luck, now we have these sequences from these cases, and with some luck, you can go back to the tree, to the phylogenetic tree of the outbreak, and say, okay, where do these sequences cluster? Yeah. And we worked closely with Andrew Rambaud, who had maintained all these sequences in Scotland. Yeah. And we sent him this sequence overnight. His answer came back, and he said, yeah. Stephan, these sequences are very close to the sequence of a survivor who survived here, the disease, end of 2014 in this area. So the epidemiologist should go to this survivor and look for a link between this survivor and these cases. Yeah? And we sent this message back to the health authorities in Guinea, Yeah? And at the same time, of course, the epidemiologists also did their job and went to these cases and took okay and went to then investigated that indeed this case had a sexual relationship with this survivor. So we came both from the molecular epidemiology and from the field epidemiology came up with the same source. And then, of course, the question was how did he transmit it? So very likely by sexual transmission. So we tested the sperm sample, and the sperm sample was highly positive for Ebola virus disease, and it perfectly fitted. So this sequence perfectly fitted with the sequence of the other. So then, of course, this was phylogenetic was done with all these sequences, and you see here this is the survivor sample, the acute sample, and here were the first cases. This is identical in sequence, the whole genome identical in sequence to the survivor semen, and there are the other sequences from the other cases here. So there is no doubt that this cluster was caused by this survivor semen, and if you look at the time scale, we are here at 500 days after onset of disease. Yeah? So our predictions about the decay is not just theory, it means there's really infectious virus still in the body of the survivors. So, and fortunately, this cluster was rapidly stopped, so the surveillance systems which had been set up in the countries worked well. This was also a spillover to Liberia then, again, quickly, so moved to Liberia, but was brought rapidly under control. So I actually have a bit hope that we won't see the epidemic of this size again in these countries. So there has been the surveillance systems and the diagnostic system really had been improved. And then, of course, the question arose: what about the evolutionary rate of the virus? Because now we know that the virus is evolving during the epidemic. So this is actually the more or less the line which depicts the number of changes. So this is more or less the number of changes by time. Yeah? And this is the acute sample, so this is perfectly on the line, but this is the sample from the seminal fluid, and that means that this has a number of mutations which correspond, it is here from 2016, but the number of mutations correspond to a date somewhere here in 2015. So that means it evolved much slower than the virus usually evolves during the epidemic, which is plausible because we assume that during virus persistence, of course, the replication level of the virus is much, much lower. And if the replication level is lower, then of course also the chance of introducing mutations or selecting for mutations is lower. So, and this means it's about 6 times lower evolutionary rate during persistence than during human-to-human transmission. This is human-to-human transmission and acute disease during the epidemic. So, and that I finished perfectly in time. Yeah. And of course, there are a lot of contributors to all these studies.
Okay, I think we should proceed with the next talk and then get questions covering the whole subject.
So while let's bring up the slides, just like to reiterate the fantastic welcome we've had over the last few days here, and thanks to Liana suggesting that we have the meeting here. The last meeting was held in January in Oxford. We're all very cold. Everyone's complaining, can we go somewhere warmer? So it was a great suggestion of Liana. So I'm head of research at in Public Health England facility in Porton Down, and we're part of a network of infectious disease laboratories throughout the UK, where we look after the internal infectious disease outbreaks and surveillance in the UK, but we also have a response element for UK government when something goes wrong, and that's why many of our people that work for us are always happy to go to do something a bit special. And I think we could, luckily Liana's that type of person, so it's glad that she became one of our PhD students last year. And so there was one Greek person on the EM lab, and she's sitting in the front row because she did 2 deployments to Guinea and helped a lot, especially with the sequencing also that we'll talk a bit about as well. So, we don't have such a nice building. This was built during the Cold War, during the bioweapons race. So it was developed for biological weapons in 1950. It was open, but then luckily we joined, and like many other countries, the convention to stop development of biological weapons, and it changed to biodefense. And we initially were part of Ministry of Defense, and in the late 70s we came to the Department of Health, which we are today, and that's why we work on public health. And this is our very modern CL4 facility here at Stonehenge, which we can see from my office window. Well, not quite, it's about 10 kilometres away. And this is obviously not the view that Liana can see, because in a different part of the city. That's Salisbury. So all very well welcome. It's a different type of beauty, not the same as your lovely island, but there's some lovely things to see as well. So, I just showed this to remind me of a few things. One is this horrible picture, but this horrible picture resulted in some significant investment into emerging diseases, because Ebola is one of those diseases which is on a category A list for the US government as a bio-threat agent, linked to increase in terrorist activity, terrorist threat. So my department received a lot of funding from the US government. Unfortunately, we didn't get a lot of money from our own government. Most of our capability and trained staff come from grants from the National Institute of Allergy and Infectious Diseases and other agencies in the US. So CBRN, which is the funding umbrella that covered EM Lab, stands for Chemical, Biological, Radiation and Nuclear Threat, CBRN. And so again, even for EM Lab, it wasn't because of doing wonderful things in the developing world, it was also defending the European countries against threat agents. So another point to raise is I'll talk a little bit about the glycoprotein, which is the target for the vaccines that have been used, and I'll talk a little about a phase 3 study that was very successful that EM Lab and Evident were part of. And a big question mark around the bat. Everyone says, oh, it's the bat that spreads Ebola. There's some evidence that there is, but still more evidence is required. And this is just summarizing some of the points that Stephan made in his presentation, but now talking more about the Evident project, which is like really the research arm of the European Mobile Lab, where many of the same members of EM Lab put together an application that Stephan led to get 1.7 million euros of funding to do research on the samples that we're able to ship back from Guinea. And I'm just going to talk about these two red ones here, but we were discussing all the progress that was made during the Evident project at the meeting here, which we've been told by our program officer from the EU has been the most profitable, cost-effective investment in a project in looking at publications that have come out of it. It's been very successful collaboration. It shows how European countries can work effectively together. And I'm saying that from a country just voted to leave the EU, but I didn't vote that way, but it's obviously a big problem for UK science now, which hopefully we'll be able to overcome. So early on in the outbreak, there was lots of scaremongering, lots of stories that the virus, this virus seemed bigger than any other one, this outbreak. It's due to the virus adapting to humans. Are there multiple exposures from the bats in the forested region, not just one spillover from animals into humans? Is it happening more than once? So this Ebola outbreak is never going to go away. So a lot of scaremongering from the press and international governments, especially WHO, who EM Lab serves, wanted to find out an accurate idea about the mutation rate, when did the virus first get introduced, and things like that. So because Stephan had a good relationship with the Guinean government before the outbreak, he was able to get permission to ship samples back to the Bernhard Institute to start a little mini biobank. And from that, we chose about 180 samples from March 2014, the beginning of the outbreak, all the way to January 2015, which was what we had in the database in the biobank at the time back in Germany. And most of the people that we chose had a high virus load because we wanted to make sure that the Illumina sequencing worked well. But that biased the death rate. So on the 180 people that we looked at, their samples, 80% of those were fatal outcomes. So we know the average is really about 50. But because the relationship between high virus load and death, we had a bit of a skewed subset of the population. And we worked closely with other collaborators in Europe who were good at sequencing, people that we worked well in the past, who had a pipeline to build the consensus sequences. The very clever people in Edinburgh University who did all the bioinformatics as well. So you saw this similar graph that Stephan showed towards the end of the outbreak to look at mutation rates in semen compared to blood. But at the beginning, this was very prized because people just didn't know how quick the virus was mutating. An earlier American study, having a snapshot of what was happening in Sierra Leone over a 3-week period, suggested the mutation rate was quite high. And what our data showed over an 11-month period, that the mutation rate was actually not that much higher than what would be expected for Ebola, knowing from history about the between outbreak mutation rate, which is about 1.42 base changes per site per year. And from this you can also work back, when did the virus spill over into the human reservoir from theoretically the bat? And so the epidemiologists, epidemiology isn't really a science, as we know. It's a bit of an art form, a bit hand-wavy, as we say. You have to ask the right question to the right people on the right day, and hopefully they're being honest and giving you the right answer. Especially when talking about sexual transmission, people don't like to give you the right answer. That may expose them to complications in personal life. So, working with Georgios Poliakos, who is at Liverpool University, concluded, and also with Andrew's calculation, that the spillover occurred around December 2013, which was nice because it agreed with the hand-wavy epidemiologists, and so everybody was happy. And we did the mutation rate, and we looked at the mutations in the glycoprotein. There were some, and we don't know what impact that would have on treatments that target the glycoprotein, like ZMapp, and also the vaccine that was being developed. And so we presented this data as soon as we had it to our masters, which is the WHO, and presented it in Conakry, where the samples obviously came from Guinea. And it showed nicely, from beast analysis, which is phylogenetics over time and also location. And this is Andrew Rambo's work. And he color-coded all the samples. Each one is a person that we took the sample from. And here we have a timeline. And this is the sort of subset of how the virus was changing, put it into some form of clade, if you like. So Guinea 1 is at the beginning. These are the early samples that were sent to Stephan based on, and the virus spread through the villages around Gekadu in the forested region. And then you can see that around about April time, but probably before, because it's only looking at the samples that we had access to sequence. So there's a lot of things went on we don't know because we don't have the samples. But it showed it came over the border, probably due to a funeral that occurred for a natural healer, and slipped down over the border into Sierra Leone, which is only about 5 kilometers away from Gekadu anyway, and caused a massive outburst in Kenema. This is the American study. It was published by Geary in Science in late 2014. But unfortunately for Guinea, it was re-exported back to Guinea, with the green nodules you'll see here. So that second wave in the forested region was much worse than the first one. And here it looks like that the outbreak from this Guinea 1 lineage was shut down. But again, this message only comes from the sequences that we did. And if you look at other samples, it may be a different story. So when I presented that data to the authorities, the they said, yeah, looks very nice. EM Lab have done a really great job. It's very interesting to see this, but it's not much good to us now. We need sequencing data, not 10 months later, we need it within 24, 48 hours. So I remembered that there's a thing called a minion, or my kids will call it obviously the minion, and it's made by a company in Oxford called Oxford Nanopore Technologies, and I know you've got one here because I saw it in a tour yesterday. And the original ones obviously have a membrane inside this cassette, in a cartridge here where you make your DNA preparation, which takes about up to 4 hours to prepare from Ebola virus. And it slips through one of 2,000 nanopores that the DNA goes through. It sets off a charge change, which is picked up by your laptop. Then you translate that charge change with some software in the cloud that you have to use that belongs to Oxford Nanopore, and then you can work out a consensus sequence from that. So using the old setup, theoretically you could sequence Ebola virus genome 20 kb in about in a couple of seconds. Now the stuff that I think you're using is the next generation. You can do it in 0.2 of a second. It's 10 times faster. And this is the basis of Liana's project. So you can correct me at any time, don't worry. So what a great thing. And if you had sequence data in real time, you could answer all these questions about sexual transmission, mutation, resistance against new drugs that we'll be using in the field, the vaccine. And Stephan gave an excellent illustration how it was used in anger. With the sexual transmission case, because a big problem was they thought it could have been a reintroduction actually from the animal reservoir, as well as another transmission chain. And so Stephan told me if the technology too good to be true. He said, "Well, try it, but it can't really work." And I said, "Oh, it's because it's British technology and not German." This is the basis. But now he knows that our technology is better than German. Even if we have to work in a glove box, not in a lovely suited CL4 facility. So this PhD student of a guy called Nick Lohman, who's a bit of a world expert on the minion, that he already had the idea to take the minion to West Africa, but had issues in trying to get out there with it. So got clearance from EM Lab that we would take this out, and he had 10 days to sort it out. But Nick is very clever. He's a medic, so he sent his PhD student, Nick Josh. And Josh had been working on the minion as part of his PhD. He arrived at the airport with 3 laptops, some Gilsons, some minions. We had a cooler box with the enzymes and things. And within 48 hours of arriving, we had a little lab at the hospital in Conakry that we were doing some clinical trials with. So don't tell anybody we did this as well. It's supposed to be all GXP. So there's a lab processing blood down here for the vaccine trial, and all he had was 2 meters of bench space. And all I did was make him cups of tea and looked after him. So he 48 hours, we got samples from Koya, ETC, the EM Lab there, Sophie Durafour, I brought them over. And he uploaded the data, Nick processed it in Birmingham, sent the information back. And immediately we knew that the samples that were circulating now in Conakry, around Conakry and Koya, actually came right from Gepidou, direct, because they were the similar as Guinea 1 lineage. We thought we'd shut down, but we hadn't. They'd gone by car, the 14-hour, 16-hour road trip by somebody who was sick, or going visiting a relative in the city, or vice versa. So immediately it had use. And the technology was then quickly tech transferred to the Koya Treatment Centre, the European Mobile Lab there. And this is where Liana spent a couple of months using the minion as well. And this is Joseph, one of our Guinean colleagues who's been working with the EM Lab for 2.5 years now. And he's now one of our PhD students that we've got funding for, along with his colleague Raymond, who also has been there from the beginning working in EM Lab. And so the sequencing capability then was being run in the capable hands of Guineans with the EM Lab staff in support. And their turnaround time from a positive sample arriving to sequence analysis being done and information provided back to the authorities was, I think the record was 18 hours, I think was the record, but usually around 24, 48 hours. And this just shows you how on the epidemiology side and the bioinformatics, you can color code the relationship of the sample that you have, and then in the databases are so important, you can then color code its closest relation. And this helps you determine where the epidemiologists should spend their limited resources, who they should be asking questions to, which prefecture they should be going to. And it also linked up with another sequencing capability in Sierra Leone using an ion torrent, where they could show that the virus was slipping across the border between Sierra Leone and Guinea, and telling the authorities that's where they should be looking at that porous border and trying to stop the movement of people, and then the transmission chains can also be reduced. And if you're sort of really clever, like these bioinformaticians in the department of Andrew Rambo, you can turn all that sequencing data, this was when they had 1,500 sequences, and you can make a video based on the phylogenetic relationship, the location of the sample, and time. And this just shows you that, so it's Gekadu, placenta, and then the time up here, it's getting a little bit more out of hand, and then until it's a cinema, when things went a bit crazy. You see this is June time, and PHE labs didn't get out there until October, November. Like a lot of the delayed response, it just illustrates that if you don't get out early and shut down the outbreaks, how dangerous it can be. So if you look at the relative investment of EM lab, which we're discussing, is about 4.5 million euros, compared to the, 2 or 3 billion euros that was spent on the outbreak and the economic impact. It's very cost-effective insurance policy to have an EM lab-like approach. And so at the end, you get a few flashes without arrows, which are probably, there's some sexual transmission cases that were probably occurring in the early days. So this only goes to October, but so Andrew needs to update it, or a student does. So quickly then, the last sort of 5-10 minutes, I'll talk about the work we've been doing looking at the immune response in people that survived Ebola and its relevance to understanding how a vaccine should work, or the optimum vaccine should work. Because the dogma suggests that if you've had Ebola, you don't get it again. I mean, I wouldn't want to put it to the test, but animal models sort of show this, and the epidemiology reports from past outbreaks show this. And also it has been proposed that plasma from Ebola virus disease survivors can also be used for therapy. So let's have a look at what's in the plasma. And past studies have been performed looking at the immune response to Ebola virus in survivors, but they've not been done comprehensively. Never had the opportunity because this outbreak is so large. And we'd like to look at the comparison, as I say, of that immune response in survivors with people who have been vaccinated with the new vaccine. So are there messages about the type of T-cell response you might get in a survivor compared to the type of T-cell response that can give protection in a vaccine? So EM Lab was involved in the phase 3 clinical trial, the ring vaccination trial, using the vesicular stomatitis virus, which is a virus of cattle, attenuated in humans, doesn't cause disease, maybe a little bit of temperature elevation. And that was constructed so it expresses the glycoprotein from Ebola virus by a Canadian company, and then in the end it was bought by Merck. All the funding came from the US government for the development. So the idea for this ring vaccination approach is copying how they helped eradicate smallpox, is that when there was a case, the WHO-led team would rush to the village, they would vaccinate 100 people around that case, all the contacts, and then monitor for future incidents in that village. And there was the control arm, which is hard to do a placebo-controlled arm in an outbreak, was those villages that they left for 3 weeks before they went and vaccinated them. I mean, obviously they still did the surveillance in those studies, in those villages as well. And the bottom line is, from this fantastic paper that was published and led by WHO, this very enigmatic and forceful Colombian doctor, Ana Maria, that showed that in those villages that you vaccinated immediately after the identification of a case, there were no new cases that were recorded post 10 days of the vaccination. And there were 16 cases in the villages where you delayed by 3 weeks before going there. So theoretically, you say the vaccine's 100% efficient, but we need more statistics, more patients, more volunteers, and that's now underway with the WHO team. They're writing up a manuscript now with bigger numbers to say if it was statistically significant or not. But this is the only vaccine that was used in anger when the outbreak was still ongoing. So this is other CDC people that also monitored the immune response in survivors back in the large 1995 outbreak. The suggestion is the antibody response can last quite a long time after the survival, after the virus has disappeared. So we set up a two-centered study, 2 cohorts with survivors in Koya, just north of Conakry, and also in Gekadu, where the EM lab was for a year as well. And we worked with the leaders of the survivors group and discussed with them the ethics behind doing the study, the patient information letters that we should give, and they helped recruit all the survivors that we used, both in Gekadu and Koya. And we also wanted to take a blood sample from these very special ladies, because these ladies help look after their sick and dying children and relatives, but they never seem to get any significant symptoms. They may have mild symptoms, but probably didn't even know they were suffering from anything untoward. But could we find signs of immunity in their blood, which would suggest that the virus had infected them, but there's something special about them that they didn't have severe symptoms. So to summarize, this is the Gekadu cohort, the Koya cohort, the numbers of survivors that we used. We had access to a number of contacts, the special ladies. We also looked at some men as well to see if they had the same special outcome as the ladies, and a number of negative controls. And we did the T-cell work in Guinea, and then shipped plasma and attempted to ship the T-cells back to Europe, where we did the subsequent analysis. So what this shows is the antibody by ELISA and T-cell and neutralizing antibody activity of the plasma from the survivors. And this was done by our EM lab evident collaborator Thomas Strecker at Marburg University. And what it shows is that you get a massive variety of intensity of neutralizing titer in the survivor. And some survivors don't seem to have much of an immune response at all. So if you were using plasma from these survivors to treat acute infected people, you may have a different outcome compared to using this high titer neutralizing antibody. This red line shows, so I had a couple of these experimental vaccines, a chimp adeno one and the VSV one, and this is my titer of about 1 in 32, which is a good titer for a vaccine. So it shows that a survivor has a much more robust, strong neutralizing antibody response compared to somebody that was vaccinated. So if you look at the contacts, these special ladies, that didn't seem to have symptoms, a lot of them do actually have immune responses. So it suggests that there was a level of replication in their blood. The PCR probably didn't detect it because the sensitivity is around 10 to the 4 genomes per mil. So it's quite likely that the genetic makeup of these individuals possibly is able to prevent them having severe disease, but still having immunity. And also a similar picture with the T cells, that the T cell response from a vaccinee 4 weeks after vaccination is down here, but it's about 10-fold higher if you're a survivor. There's a correlation with a strong T cell response and a strong antibody response, and also those survivors where we saw antibody in the contact, we also saw T-cell response as well. And then you look at how long did that immune response last for. So this grouping the volunteers into time post-survival. And if you look at antibody or T-cell response over that 1 year period, the T-cell response really is quite level. So it does not seem to wane, which again was a bit surprising. But is it because the virus is seeping back from the semen into the bloodstream and reactivating the T-cell response? It's a possibility. So in summary, early detection of outbreaks is extremely important for the success in keeping the outbreak raging out of control. That we can do clinical trials in the middle of an outbreak if you have a good laboratory support. That survivors seem to have very, very robust immune responses, but they seem to have a similar pattern of immunity induced by the vaccine. And the immune responses we see in the direct contact suggest that many more people were actually infected than was recorded, but didn't seem to show significant symptoms. And as for Stephan, lots and lots of very important people that all played a significant role in the collaborations. But a special thanks to the people in Guinea for volunteering for our studies and for collaborating with us. And obviously many people gave up their time, and thank you for all the volunteers as well. Thank you.